Hello everyone, welcome to Civil Engineering by Sunshine Academy YouTube channel. Today we are entering into chapter 2, Precipitation. What is precipitation? Water evaporates from oceans. It forms clouds. Clouds becomes heavy. Water falls down. That falling water is called precipitation. Not only rain, anything that falls from clouds in liquid or solid form is precipitation. Rain, snow, hail, drizzle are forms of precipitation. Precipitation is any form of water that falls from atmosphere to Earth's surface. Why does it rain? Imagine the air is like a glass. This glass doesn't hold liquid water. It holds invisible water vapor. The glass has a capacity. In physics, we call this saturation vapor pressure. Saturation vapor pressure is the maximum water vapor the air can hold. Let's call it PS, the air's full capacity. Now, how much water vapor is actually inside the air right now? That's called PA, actual vapor pressure. So, think like this. PS equals to glass size, saturation vapor pressure. PA equals to water inside the glass, actual vapor pressure. If PA is smaller than PS, the glass is not full. So, no rain. But what happens if PA becomes equal to or greater than PS? The glass overflows. That overflow is rain. Now here is the magic part most students miss. Temperature controls the size of the glass. When temperature is high, the glass becomes big. Air can hold more water vapor. When temperature decreases, the glass shrinks. Capacity, saturation water vapor decreases. But the actual water vapor is still there. So what happens? Small glass, same water, overflow, then rain. Have you noticed? Hot afternoon, no rain. Evening becomes cooler. Suddenly rain starts. Why? Because the air cooled down. The glass shrank. Overflow happened. That's precipitation. So rain is not magic. It's just physics. When temperature falls, the air's capacity shrinks and the sky overflows. That's it. Simple. Relative humidity. Relative humidity is the ratio of actual water vapor present in air to the maximum water vapor it can hold at the same temperature expressed as a percentage. Relative humidity equals to actual vapor pressure by saturation vapor pressure into 100. RH equals to PA by PS into 100, where PA equals to actual vapor pressure, PS equals to saturation vapor pressure. Imagine the air is a glass. It holds invisible water vapor. Now listen carefully. The size of the glass is called PS, saturation vapor pressure. That means maximum capacity. And the water already inside the glass, that is PA, actual vapor pressure. So simply PS equals to glass size, PA equals to water inside the glass. Relative humidity is just one question. How full is the glass? RH equals to PA by PS into 100. That's it. It is just the percentage fullness of the glass. If the glass is 50% full, RH is 50%. 80% full, RH is 80%. 100% full, air is saturated. And when it reaches 100%, the glass can't hold more water. So what happens? It rains. If PA is less than PS, the glass is not full. No rain. Simple. Here is the most important concept. Temperature controls the size of the glass. When temperature is high, glass becomes big. Capacity increases. Relative humidity becomes low. When temperature drops, glass becomes small. Capacity decreases. But the water inside hasn't changed. So what happens? Same water, smaller glass. Now the glass becomes full. Relative humidity increases to 100%, and that leads to rain. So remember this forever. If temperature decreases, capacity decreases. Then relative humidity increases. Then it will result in rain. Types of precipitation. There are 4 types of precipitation. 1. Convective precipitation. 2. Orographic precipitation. 3. Cyclonic precipitation. 4. Frontal precipitation. Why does it suddenly rain heavily on a hot afternoon? That's called convective precipitation. Let me explain it simply. First, the sun heats the ground. When the ground becomes hot, the air above it also becomes hot. Now remember one rule. Hot air is lighter. So what does lighter air do? It rises. As this warm air rises higher into the atmosphere, the temperature starts decreasing. Higher altitude means cooler air. Now here is the important part. Cool air cannot hold as much water vapor as warm air. So the water vapor starts turning into tiny water droplets. This process is called condensation. When millions of droplets gather together, clouds form. Usually these are tall cumulonimbus clouds. Inside these clouds, droplets combine and become bigger and heavier. And when they become too heavy to float, they fall as rain. And because the rising air is strong and vertical, the rainfall is usually heavy and short duration. That's why you see sudden afternoon showers in tropical regions. Convective precipitation happens due to surface heating. Warm air rises vertically, air cools, condenses, and produces heavy rainfall, common in tropical areas. So remember this. Sun heats ground, warm air, warm air rises, cooling, condensation, then heavy rain. That is convective precipitation. Why do mountains receive heavy rainfall on one side, while the other side remains dry? That phenomenon is called orographic precipitation. Imagine moist air is moving towards a mountain. The mountain acts like a giant wall. The air cannot pass through it. So what happens? The air is forced to rise upward along the mountain slope. Now remember an important rule of atmosphere. When air rises, temperature decreases. As the rising air becomes cooler, it cannot hold as much water vapor. So the water vapor starts condensing into tiny droplets. Clouds form. As more condensation occurs, droplets become bigger and heavier. Finally, they fall as rain on the windward side of the mountain. This side receives heavy rainfall. Now, what happens after the air crosses the mountain? The air moves down the other side. As it descends, the air becomes warmer and drier. Because of this, very little rainfall occurs on this side. This dry region is called rain shadow region. Orographic precipitation occurs when moist air is forced to rise over a mountain barrier. On windward side, heavy rainfall occurs. On leeward side, less rainfall occurs. It is a dry region, rain shadow region. So remember this simple idea. Mountain barrier, air forced to rise, cooling and condensation, rain on windward side. That is orographic precipitation. Cyclonic precipitation. Have you noticed that during a cyclone or low pressure system, rain falls over a large area? That rainfall is called cyclonic precipitation. Let's understand it in a very simple way. Cyclonic precipitation occurs in a low pressure system. In a low pressure area, air from the surroundings starts moving towards the center. This movement of air towards the center is called convergence. Now, when all this air meets at the center, it cannot go downward. So what happens? The air moves upward. And remember the basic rule. When air rises, temperature decreases. As the air cools, it cannot hold as much water vapor. So the water vapor starts turning into tiny droplets. This process is called condensation. Clouds form. As the droplets grow bigger and heavier, they fall as rain. Because a cyclone covers a large area, the rainfall is usually widespread and continuous. Cyclonic precipitation occurs due to rising air in a low pressure system. Air converges towards the center, then air rises, then cooling, then condensation, and finally rainfall. In the northern hemisphere, cyclones rotate anti-clockwise. In the southern hemisphere, cyclones rotate clockwise. So remember this simple flow. In a low pressure system, air converges towards the center, then air rises, then cooling, then condensation, then finally rainfall. That is cyclonic precipitation. Precipitation mainly occurs in two forms, rain and snow. Rain is liquid precipitation where water droplets fall from clouds, usually having a size between 0.5 mm and 6 mm. Based on rainfall intensity, rain is classified as light rain when the intensity is less than 2.5 mm per hour. Moderate rain occurs when rainfall intensity is between 2.5 and 7.5 mm per hour. Heavy rainfall occurs when rainfall intensity is greater than 7.5 mm per hour. Snow is a form of precipitation that occurs when water vapor in the atmosphere changes directly into the ice crystals, which then fall to the ground. Snow generally occurs in very cold regions, such as polar regions and high mountain areas. Snow is actually very light and fluffy. Why? Because there is a lot of air trapped between the ice crystals. Due to this trapped air, then the density of snow is very low, about 0.1 gram per cubic centimeter. In simple words, snow is much lighter compared to solid ice. Finally, how do we measure snowfall? Since snow is fluffy, meteorologists usually melt the snow into water and measure its depth, or they estimate it using the assumed density. So remember three simple points. Snow forms as ice crystals, it has very low density, and snowfall is usually measured by melting it into water depth. Now we discuss four minor forms of precipitation. They are drizzle, glaze, that is freezing rain, sleet, and hail. They mainly differ by two things. One, size of particles. Second, temperature conditions. Think about drizzle. Look at the image. It says size is less than 0.5 mm and very low intensity. One small question for you. If drizzle droplets are extremely small, that is less than 0.5 mm, would a drizzle feel like heavy rain or more like mist or light spray? It feels like a mist or a light spray. Why? Because the droplets are very tiny, less than 0.5 mm, and they fall very slowly. Intensity of rainfall is less than 1 mm per hour. So it feels like a gentle spray rather than normal rain. Good. Now let's move to the next type, glaze, freezing rain. Look at the slide. It says freezes upon contact with cold ground, 0 degrees centigrade. Think about the process. Rain falls as liquid water from the cloud. The ground or surface is below 0 degrees centigrade. When the raindrops touch the cold surface, they immediately freeze. So it forms a thin layer of ice called an ice sheet. Now one small question. If roads gets covered with this ice sheet, what problem do you think vehicles will face? Vehicles will slide because glaze forms a thin, smooth ice layer on roads. The friction between tires and the road becomes very low. So vehicles lose grip and starts sliding, which makes driving very dangerous. The third type is sleet. Sleet is basically frozen raindrops. When raindrops pass through a very cold layer of air, they freeze before reaching the ground. These frozen droplets appear as small translucent or transparent ice pellets, usually less than 5 millimeters in size. Finally, we have hail. Hail consists of hard balls of ice, usually larger than 5 millimeters and sometimes even reaching 50 millimeters in diameter. Hail forms inside strong thunderstorms, where ice particles grow larger by repeatedly moving up and down in powerful air currents. Because of their large size and hardness, hailstones can damage crops, vehicles, and buildings. So remember these four minor forms, drizzle, glaze, sleet, and hail, each formed due to different temperature conditions and particle sizes. Now let's understand how rainfall is measured. For this, we use an instrument called a rain gauge. It is also known as hytometer or ombrometer. The main purpose of a rain gauge is very simple. It measures the depth of rainwater that falls on the ground, usually in millimeters or centimeters. Rain gauges are mainly divided into two types. The first type is non-recording rain gauge. This type only measures the total rainfall over a period of time. It does not record how rainfall changes during the storm. A common example is the Symon's rain gauge, which is widely used and usually read once daily. The second type is recording rain gauge. This type automatically records how rainfall varies with time. There are three common types: natural siphon rain gauge, tipping bucket rain gauge, and weighing bucket rain gauge. In India, there is a standard practice for rainfall observation. The rain gauge reading is taken every day at 8:30 am. So remember the key idea. A rain gauge measures rainfall depth and it can be recording or non-recording, depending on whether it records rainfall over time or not. Now let's understand the Symon's rain gauge, which is a non-recording rain gauge. First remember that this is the most commonly used rain gauge in India. At the top there is a circular collector funnel. The diameter of this collector is 127 mm, which is about 5 inches. This funnel collects all the rainwater falling over that area. The collected rainwater then flows through the funnel and is stored in a bottle inside the outer casing. Since this is a non-recording rain gauge, it does not continuously record rainfall during the storm. Instead, the observer manually checks the collected water once a day. The important point to remember is that Symon's rain gauge measures only the total rainfall depth, not the rainfall intensity or variation with time. The entire rain gauge is usually installed on a concrete base of about 60 into 60 cm to keep it stable and properly positioned. So remember three key points. Symon's gauge, its diameter is 127 mm, that is 5 inches, which measures total rainfall, not intensity. Now let's understand the rules for placing a rain gauge station. When we install a rain gauge, the most important thing is that nothing should block the rainfall. If trees or buildings are too close, they can interfere with the rain reaching the gauge. So engineers follow a simple golden rule. The distance between the rain gauge and any obstacle should be at least twice the height of that obstacle. In simple terms, distance d must be greater than or equal to 2 times the height h. There is also another condition. The distance should not be less than 30 meters. So we always choose whichever value is greater, either 2h or 30 meters. Next, the rain gauge should be placed on open ground, so rainfall can fall freely. The foundation should be level and stable so that the instrument remains accurate. Also, there should be no overhanging branches because leaves or branches can block rainfall. Finally, the rain gauge is usually protected with a small fence around 5.5 meters by 5.5 meters to prevent disturbance from animals or people. So remember the key idea. Place the rain gauge in open ground, away from obstacles. Following the rule, D should be greater than or equals to 2h or at least 30 meters. Now let's understand a recording rain gauge, specifically the natural siphon rain gauge, which is the standard recording rain gauge used in India. First, rainwater enters the instrument through the rainwater inlet and collects inside a chamber. Inside this chamber, there is a float. As rainwater collects, the water level rises and the float also rises. This float is connected to a rod and a pen. So when the float moves up, the pen also moves upward. Next to it, there is a rotating drum covered with graph paper. This drum rotates slowly with the help of a clockwise mechanism. As the drum rotates and the pen moves upward, the pen draws a line on the graph paper. This line shows how rainfall accumulates over time. This graph is called a mass curve, which represents cumulative rainfall versus time. Now here comes the special feature.
When the chamber becomes full, a siphon tube automatically drains the water out. Once the water is drained, the float drops down, the pen returns to its starting position, and the process starts again. So the instrument continuously records rainfall automatically. In simple words, rain enters, float rises, pen moves, graph is drawn, chamber fills, siphon drains, pen resets, and this cycle repeats to give a continuous record of rainfall over time. Now let's understand another recording rain gauge called the tipping bucket rain gauge. The working principle is very simple. First, rainwater enters through a funnel at the top and flows into a small bucket system placed on a pivot. There are actually two small buckets balanced like a seesaw. When rainwater fills one bucket, it collects up to a fixed amount, usually 0.25 mm of rainfall. Once this amount is reached, the bucket becomes heavy and tips downward. When the bucket tips, two things happen. First, the water empties out and the other bucket moves into position to start collecting rain. Second, the tipping action closes an electric circuit, producing a small click signal. Each tip corresponds to a fixed amount of rainfall, like 0.25 mm. By counting the number of tips, the instrument automatically calculates the total rainfall and rainfall intensity. Because it sends electric signals, this rain gauge can transmit data remotely using telemetry. That's why it is very useful in remote or inaccessible areas. So the process is very easy to remember. Rain enters, bucket fills, bucket tips, electric signal generated, next bucket starts filling, and this repeats continuously to measure rainfall automatically. Now let's look at the third type of recording rain gauge, called the weighing bucket rain gauge. The working principle here is very simple. Instead of measuring rainfall by tipping or siphoning, this instrument measures the weight of the collected rainwater. Rainwater falls into a bucket placed on a weighing mechanism, usually supported by a spring system. As more rainwater collects, the weight of the bucket increases. This increase in weight moves a mechanical linkage connected to a pen. The pen records this change on a rotating drum covered with graph paper. The instrument then converts the weight of the collected water into rainfall depth, giving a continuous record of rainfall. One important advantage of this rain gauge is that it does not have moving water parts like tipping buckets or siphon tubes. Because of this, it does not get clogged by ice. That is why the weighing bucket rain gauge is the only rain gauge suitable for measuring snow and hail. So remember the idea simply. Rain collects, weight increases, pen records, weight converted to rainfall depth. Now let's understand how rainfall data is represented using graphs. There are two important graphs used in rainfall analysis, the mass curve and the hydrograph. First, the mass curve. A mass curve shows cumulative rainfall versus time. This means it represents the total rainfall accumulated from the beginning of the storm up to a certain time. On the graph, the vertical axis represents cumulative rainfall and the horizontal axis represents time. On the graph, the vertical axis represents cumulative rainfall and the horizontal axis represents time. An important point to remember is that the slope of the mass curve represents rainfall intensity. If the curve becomes steeper, it means the rainfall intensity is higher. If the curve becomes flatter, the rainfall intensity is lower. The mass curves are usually obtained from natural siphon rain gauges or weighing bucket rain gauges. Now let's look at the hydrograph. A hydrograph shows rainfall intensity versus time. It is usually represented using vertical bars. Each bar represents the rainfall intensity during a particular time interval. An important concept here is that area under the bars represents the total rainfall depth during the storm. Hydrographs are commonly obtained from tipping bucket rain gauge. So remember the difference clearly. Mass curve, cumulative rainfall versus time. Hydrograph, rainfall intensity versus type. Now let's understand rain gauge network density, which is given in IS code 4987. Network density simply means how many rain gauge stations should be installed in a given area to measure rainfall accurately. The number of stations depends on the type of terrain and rainfall conditions. First, consider flat or plain areas. Since rainfall variation is usually smaller here, fewer stations are needed. According to the code, we install one rain gauge station for about 520 square kilometers. Next, in plateau regions, rainfall variation is a little higher compared to plains. Therefore, the network density is increased. Here, we provide one station for about 260 to 390 square kilometers. Finally, in hilly areas or regions with heavy rainfall, rainfall varies significantly from place to place. So we need more stations for accurate measurement. In such areas, we install one station for about 130 square kilometers. There is also an important general rule. At least 10% of the total rain gauges in the network must be recording type rain gauges, so that rainfall variation with time can be measured automatically. So remember the key idea. In plains, we require one station per 520 square kilometers. In plateau, one station per 260 to 390 square kilometers. In hills or heavy rainfall region, we need one station per 130 square kilometers. And at least 10% gauges should be recording type. Let's quickly revise chapter 2 using this cheat sheet. First, let's look at the key numbers you should remember. The size of rain droplets generally ranges from 0.5 to 6 millimeters. If the droplet size is less than 0.5 millimeters, it is called a drizzle. Next, the diameter of Symon's rain gauge collector is 127 millimeters. In India, the standard time for taking rain gauge readings is 8:30 am every day. For proper installation of a rain gauge, we follow the placement rule. The distance from any obstruction should be at least twice the height of that obstruction. Now let's match the gauge types with their functions. The Symon's rain gauge is a non-recording rain gauge and is the standard rain gauge used in India. The natural siphon rain gauge is a recording type, also called the float type rain gauge. The tipping bucket rain gauge is mainly used for remote monitoring and for measuring rainfall intensity. Finally, the weighing bucket rain gauge is the only gauge suitable for measuring snow and hail. If you like the video, please like, share, comment and subscribe. Thank you. Don't forget to subscribe my channel.